Welcome back to computer graphics and visualization subject. In that module 3 we are discussing module 3. Yesterday we have discussed on 3D geometric transformation. In that we have discussed transformation, rotation about an arbitrary axis. Today we will start with the color models. Right, in that color models, first topic is properties of light. What is a light? Means whatever our eye sees normally, that is light in general, but as per the definition, light is a electromagnetic spectrum which has a narrow frequency band. Right, in that frequency only our eye will means normally human eye sees, that is called light. Each frequency value within the visible range, that is a light spectrum, visible range of the electromagnetic spectrum, corresponds to distinct spectral color. Means every wavelength, every frequency value will generate different color in that spectrum, which our eye can visualize. The electromagnetic spectrum range starts from, in lower side, 3.8 into 10 to the power 14 hertz, then higher side 7.9 into 10 to the power 14 hertz. The lower side normally looks, our eye sees as a red color. In higher side normally the spectral color is violet, as you can see on screen. Means that total range 700 nanometer to 400 nanometer, that is towards lower side, that is towards 3.8 into 10 to the power 14 megahertz, the color of light looks like red. Then towards 7.9 into 10 to the power 14 hertz, that is higher side, it will look like violet. Only in this spectral our eye will visualize the light. Other spectrals are not. Ultraviolet and infrared, our eye is very sensitive. There is again on our spectrum wavelength, that is infrared wavelength and infrared light and ultraviolet lights. Our eyes are very sensitive towards those lights. That's why only with the naked eye we can see light in this range, that is 3.8 into 10 to the power 14 hertz to 7.9 into 10 to the power 14 hertz. Right. Then in the wave model of electromagnetic radiation, light can be described as oscillating transverse electric and magnetic fields propagating through a space. Means in a space these oscillating transverse electric and magnetic fields are propagating. Right, for each spectral color the rate of oscillation of the field magnitude is given by the frequency f. Means for each spectral color, whatever color we are talking about, the rate of oscillation of the field magnitude is given by the frequency f. Right, frequency f. Then the time between any two consecutive positions, on the wave that have the same amplitude is called the period. Means the period is nothing but the in a wavelength at a same amplitude, two consecutive same amplitude gap is called period, that is t of the wave, which is the inverse of the frequency, that is t equal to 1 by f, as you know. Right, and the distance that the wave has traveled from the beginning of one oscillation to the beginning of the next oscillation is called wavelength. Means the top amplitude, means one amplitude at the same level to the other amplitude at the same level is called the wavelength, that is lambda. That's why the speed of light c is calculated as lambda into f, means wavelength into frequency, means how much the length of one wave and what speed that light is traveling is called speed of light. Understood? The length of each wavelength, how much length each wavelength is taking to traverse complete one cycle, then how much such cycles in 1 second, that is called speed of a light. A light source such as the sun or the standard household light bulb emits all frequencies within the visible range to produce a white light. Means whatever our eye sees, whether it may be seen from the sun or it may be seen from the house lights, bulb, whatever, tube light, whatever, those sources will generate all the lights with equal frequency. If you combine all the lights with equal frequency, then the result of those lights will be automatically white light. That's why we are able to see light color as a white light, because the all colors are mixed with equal frequency in that light, whether it is from sun or whether it is from bulb. All light frequencies are mixed equally. That's why the equal mixture of all colors is gives white light, right? This is white light. Regarding light, when white light is incident upon an opaque object, when white light is incident upon an opaque object, some frequencies are reflected and some are observed. Normally whenever light falls on any of the object or opaque object, some of the frequencies are reflected and some are observed by, depending on the what type of object that light is falling, right? The combination of frequencies present in the reflected light determines what we perceive as the color of the object. Means when it is light is falls on any object, then some frequency of that light is observed, then some frequency of light is reflected. Then what our eye sees, that is a reflected light. The reflected light determines what we perceive as the color of the object. Means whatever you are seeing after reflection, whatever your eye sees after reflection, normally that is color of light. That is color of light, color of object. If low frequencies are predominant, if low frequencies are predominant in the reflected light, the object is described as red. Normally the red light is towards 3.8 into 10 to the power 14 hertz. If the low frequencies are predominant, means they are dominant in the reflected light, whatever light is reflecting towards your eye, if that area means lower side areas are predominant, then normally the object is described as a red light, right? Then in this case we say that the perceived light has a dominant frequency. Means which color object you are seeing, nothing but that color is dominant, that color light has a dominant frequency or dominant wavelength as the red end of the spectrum. That's why towards lower side, means 3.8 into 10 to the power 14 side, normally the color of light is red, as you can see in that spectrum here. Toward this end the color of light is red, right? That's why that is normally that is a dominant frequency if that is more in reflected light. The dominant frequency is also called the hue or simply the color of the light. In some of the textbook, the dominant frequency is called the hue or simply the color of light. Then next, psychological characteristics of a color. Normally when we view a source of a light, normally when with the naked eye, whenever we are viewing a source of a light, our eyes respond to the color. Normally our eyes will respond to the color. That color is dominant frequency, means which color our eye responds, normally that color light is dominant in that, and two other basic sensations along with that color of a light our eye looks, our eye sees. Along with that again there are two type of basic sensations, one is brightness, one is purity. Then what means these are the again properties of that light, right? Brightness means which corresponds to the total light energy, and can be quantified as the luminance of light. Means total light energy, how much that particular color energy is there in that light, that is the brightness. If the blue color is more, nothing but blue color bright energy is more in that light, that is brightness, right? Then purity or the saturation. Purity describes how close a light appears to be a pure spectral color such as red. Means purity means you can observe in a red we have dark red, bright red, light red, like this. That is called purity. If purity will describe how close a light appears to be a pure spectral color, example is red, whatever blue, green, that is called purity, right? That is saturation. Means after that we don't have any other red, that is the last stage of red color. Once you pursue the last stage of red color, that is called a purity. Means there is no change, only if you want you can decrease the color, but you cannot increase the purity of that color, that is called the purity. Another term, chromaticity, is used to refer collectively to the two properties describing color characteristics, purity and dominant frequency hue, right? Then next, then how to calculate this one? How normally how that color, which color that light is, what is the white, when white light will appear, when the other colors of the light you can see, that is what white light. Example, this is the white light. Your my top left picture is white light, means energy distribution for a white light source. If you see that, as you know, the lower end is red, higher end in that spectral is violet. If in that range red to violet, if all these spectrals have equal frequency, equal energy, if you mix all spectrals with the equal energy, normally as I told, you will get a white light. If all the spectral frequencies have equal energy, then normally you will get white light, right? We can calculate the brightness of the source as the area under the curve, which gives the total energy density emitted, right? Purity, that is saturation, depends on the difference between ED and EW. Right side means right side picture, dominant frequency light, that is right side picture. You can see that there is a EW and ED. EW means white light, ED means dominant light, right? Again, from red to violet, if you mix equally all the light, if you mix equally, you will get white light. Then again, depending, pure white, again light white, like that. Means again in white we have different range of whites, right? There somebody may tell that yes, this white is different, then that white is different. That depends on what the energy level. Depending on the energy level, you will get purity of that white light again, right? That purity depends on the difference between ED and W. Means purity again in the sense that white light also, what quantity of energy you are adding, that depends on the again purity of white light. The larger the energy ED of the dominant frequency component to the white light component EW, the higher the purity of the light. For example, ED is dominant frequency compared to the white light component EW, the higher the purity of the light. At that time, if your white energy is less compared to dominant energy, if your white light energy is less compared to dominant energy light, then definitely that color light has brighter. That if means in the white, normally you are mixing all colors, normally the spectral is appeared in all colors, but in that spectral, white color mixture quantity is less. For example, 0.5, 0.5, 0.5, all you have mixed, but red color you have mixed with 10. Assume that 10 units, means 0.5 unit, 0.5 unit, 0.5 unit, 0.5 unit, you have mixed all colors, but red color you have mixed with 10 units. At that time, the dominant frequency is 10, right? That is the meaning of that. The higher the purity of that, means that time red is pure, right? We have a purity of 100%, means for example, when do we say purity of 100%? When EW is 0, there is no white, means you have not mixed any other color other than your interested color. For example, you want pure red. When you want red, you don't mix other colors, right? If you mix other colors, you will get white. If you mix other colors equal amount, you will get white. Again, it depends how much quantity you will add, that much purity you will get. When you want only dominant purity of any color, then you don't mix any other colors along with that, only take as a red, right? That time, that is EW. White is 0, and that is what? Pure. And purity of other purity of the 1 minute, purity of 0 0% when EW equal to ED. Purity of 0 means you will not find any purity. Normally you will find white. Means you will not differentiate other colors in that. If you are able to see only white color, at that time all colors you have mixed equally, definitely you will get, there is no pure. Normally you will see white color. There is no red, there is no blue, there is no other color, only always you will see white color, because all colors you have mixed equally. Once you mix all colors equally, then normally it yields a white color. At that time, when EW is equal to ED, normally there is no purity, means you cannot differentiate what color. Normally you will see that is a white color. This is regarding property of color, property of light. Then next, now we'll move to color model. What is a color model? A color model is an orderly system, means there is some system for creating a whole range of colors from a small set of primary colors. Means there is some system exists in basically computer science, that is called a color model, right? By using some primary colors we are creating whole range of visible colors which our naked eye can see, right? There are two types basically again in this color model. Basically there are two types of color models, those are named as subtractive color model, then one more is called additive color model. There are basically two categories, subtractive and additive color models. What do you mean by additive? Additive color model use light to display color, means we are using a light rays to display color, while subtractive modes use printing inks. Subtractive color will use printing inks. In detail we will discuss in next slides, right? Printing inks. Color perceived in additive models are the results of transmitted light. Again, colors seen by our naked eye are result of the transmitted light, right? Transmitted light. Color perceived in subtractive models are the result of reflected light. There is a difference between additive and subtractive light. In additive model, whatever you are seeing, that is a transmitted light. Directly you are transmitted from some source, that is transmitted light. In subtractive model, whatever light, whatever color or whatever light you are seeing, whatever color you are seeing, that comes from the reflected light. Means that light fallen on some object, then that has reflected. That is what subtractive model, right? Then color models. There are several established color models used in computer graphics. Again, there are many color models available in computer graphics, but the two most common are the RGB model, that is red, green, blue, for computer display. This is for display purpose. Then nothing but these are for monitors, any electronic device. That monitor may be any electronic device, it may be computer, it may be laptop, it may be TV, it may be your mobile display, whatever. That is, those type of devices will use RGB color model. Then one more is CMY. Again in that CMY, that is CMYK. Basically there is one CMY, then again that is categorized in CMYK model, that is cyan, magenta, yellow, then sub of CMYK, that is a black for printing. Means whenever you want to print something on a paper by using a inkjet printer or whatever printer, those type of devices will use CMYK color model, right? You can see the color model below with the figure, that is subtractive color CMYK, right? Next one is additive color RGB. Now we'll discuss one by one. RGB color model, red, green, blue color model. RGB is an, as I told, additive color model for computer display, use light to display color. Means as I told, these are for display purpose, electronics displays. That may be computer monitor, that may be your TV monitor, that may be your laptop monitor, whatever, mobile monitor, whatever, right? We are using light to display color. Colors resulted from transmitted light. Here we are displaying color by transmitting light. I think you can remember, you can recall the CRT cathode ray tube, CRT tube, when we were discussing CRT tube. In that colored light one animation I have shown, there are 3 electronic guns. Through that gun we are transmitting light, then they will fall on 3 different dots of a pixel, those red, green, blue. Then that is what means we are transmitting light on those, then those transmitted light will give you the proper color, red plus green plus blue. If you are sending equal amount of red, green and blue light on your monitor, for example 10 units of red color, 10 units of green color, 10 units of blue color, if you are transmitting on your monitor, then that dot, whatever pixel which contains these RGB dots in that color monitor pixel, don't normally that pixel you look as a white color. Means if you mix equal amount of red, green, blue color, then that yields white color. In right side you can see there is RGB, the combination of 3, there is a space, that is white color, right? If you mix equally RGB, you will get white color. You can observe in that figure whatever you are displayed in this monitor. Then next, CMYK color model. CMYK, that is a, as I told, subtractive color model. Means in RGB, by adding colors we are getting different colors. Means we will add the colors to get a different color. In CMYK we will subtract colors to get the other color. That is the difference. We will see how that will happen. This is standard color model used in offset printing, as I told. Whenever you want to print something on a paper, right, at that time definitely those devices will prefer CMYK color model for full color documents. Because such printing uses inks of these 4 basic colors. Normally those printing devices will use 4 basic colors. It is often called 4 color printing. What are those 4 basic colors? 4 basic colors in below I explain. Where 2 colors of RGB overlaps, we see a new color formed by mixing up these 2 additive primaries. As I told, whenever 2 RGB colors overlap, in previous slide you have seen, whenever you are overlapping 2 RGB colors, you will get a new color by mixing those color primaries. These new colors are, after mixing RGB colors, definitely we are getting new colors. So those new colors are a greenish blue called cyan. A greenish means if you mix green and blue, you will get a cyan, right? If you mix blue and red, that is bluish red color, magenta. Then a bright yellow. Then the last color, the key color is black. If you mix this cyan, magenta, yellow equally, then you will get a black color, right? Again black, again that varies how much quantity you are mixing. Depending on that, again in black you can vary the brightness, right? This is CMYK color model. Then CMYK color model, we can express this mathematically. If you want to express this mathematically with a pseudo algebraic writing, normally we will write R in red in R, green in G, B as blue, that is red and green, C as cyan, M as magenta, and Y as yellow, cyan, magenta and yellow, and W for white, and plus is for additive and minus is for subtractive. Light up we have. If you see this figure, right, primary colors are, normally we have used red, blue, green. These are the primary colors, red, blue, green. If I add green and blue, what color we got? We got cyan. That is green plus blue equal to cyan, or one more way is white minus red. If you observe this diagram, basically that is white. If you remove red from white, that is also cyan, right? You can represent in both the ways, that is green plus blue or white minus red. That is what subtractive. White minus red is subtractive, means white color if it absorbs red, then you will get cyan color. That is what subtractive. Then magenta, if you use additive, if you are using additive, then R plus red plus blue if you have to add. If you mix red plus blue, then you will get magenta. Or if you subtract green from white, means basically your background is white. From white, if you subtract green, then you will get magenta. That is subtractive. You can form colors in both the way. If you want, you can go by additive, or if you want, you can go by subtractive. But there is a difference, right? Then yellow, that is R plus G, red plus green will yield yellow. That is additive model. Or from white, if you subtract blue, you can see that image, right? If from white, if you subtract blue, that time also you will get yellow. You see there, right? Basically center is a white, then from white, if you remove blue, area from white, only left is yellow. Similarly, for magnet, from white color, that is from center, if you remove yellow area, green area, whatever green region is there, if you remove entire green region from that yellow, from that white, then you will get magnet, right? Like that cyan, right? In each equation, the color on the left is called the complementary color of the one at the extreme right. That is complementary, means if you want you can get it by adding, or if you want you can subtract it by white, right? That is what complementary of right. For example, magenta is the complementary color of green. Magenta is the complementary color of green, means if you remove green from white, then you will get magenta, right? Because how you got green, green you got by adding, green you got by adding previously. How you got a green? You got green by adding cyan and yellow, right? That's why if you do this complementary, then you will get the other colors. Then next, the process of reflection. Then how our eye perceives this? How our eye perceives this? When we talk of cyan ink, for example, if something you have printed on paper, but that print color is cyan, how you observe that? How your eye sees that yes, that printed is cyan color, right? What happens here? When you are seeing the cyan ink on paper, we mean that when it is applied to white paper, normally where you are printing, we are printing it on white paper. We are printing it on white paper and illuminated by a white light. We are printing on white paper, then we are illuminating, means we are transmitting white light on that. We are transmitting white light on that. White light, we are illuminated by a white light, will absorb the red component. That paper will absorb the red component. That paper, white paper, will absorb the red light, red component, then allowing the green and blue. Only it passes the green and blue, because we are using CYM model. Then it passes only green and blue, which combine to produce a cyan. If you green and blue, if you mix green and blue, then definitely you will get a cyan color to be reflected back, right? If you see this one, incident light is white. Normally whenever light is coming from any source, it may be bulb or it may be sun, light comes in a white color. Why it is coming in a white color? Because all colors you have mixed equally. All colors you have mixed equally, right? White light is coming, then it falls on white paper, then it falls on white paper, then there is a layer of cyan ink, then there is a layer of cyan ink. That cyan ink layer will absorb red light. That cyan ink layer will absorb red light. Once it absorbs red light from white light, only light left are from RGB, only light left is red light is absorbed. Only right light is coming is green and blue. Red light is absorbed by that layer, right? On white paper, red light is absorbed. Then only light emitted from, reflected from that is only green and blue. Green and blue will produce a cyan color. That's why you are observing only cyan color is printed on that paper, right? This is one example. Then one more example. If you apply a layer of such an ink to white paper and then add a layer of yellow and yellow, the yellow ink will absorb incident blue light. Normally yellow ink will absorb incident blue light. So the combination of the cyan and yellow inks produce a green light color. Means in general, if somebody is standing, some guy is standing on sunlight with red shirt, some guy is standing on sunlight with red shirt, then sunlight falls on that guy, his shirt, then you are observing his shirt is a red color. Why his shirt is a red color? Because that shirt has absorbed green and blue. That shirt normally will absorb green and blue color from the white light, then it will only reflect the red light. That's why you are observing red light. Means it has subtracted from white light, it has subtracted red. It has, if that his weared shirt is a red color, the white light will fall on, when you stand in sunlight, white light will fall on that his red color shirt. The red color shirt will absorb only green and blue color light from that white light, because that white light is a mixture of red, green, blue. If you mix red, green, blue equally, then you will form white light, right? It will absorb the red and green and blue, only it will reflect the red color. That's why you are observing red color. Same with blue color, whatever color if you take, if that is a subtractive model, same concept they have explained here, right? Similarly, combining cyan and magenta inks produce a blue. As you know, if you combine cyan and magenta inks, will produce a blue. A combination of all three colors will absorb all incident light, producing black. If you are using a if on any paper, if it observes all the colors, if it observes all the colors in CMY, if any paper observes all three colors, then that part is black. You can observe in this image, right? If that particular paper is observing with all colors, if it observes all colors, then that part will look a black color, right? That's why basically whenever we are printing, normally most of the time newspapers, whatever inkjet printers we are using, we will print it on white. We are printing it on white shades. That's why white is mixture of all colors equally. RGB colors will be mixed equally, then it will form a white color. Then whenever we are displaying on display monitor, if you without switching on monitor, the monitor will be in black color. Then when you mix equally in particular light equal amount, then that particular monitor you will feel white color. This is what in that subtractive and additive model. Then same like magneta, the subtractive color model in detail. Dye color absorbs, reflects. In short, if your dye color is cyan, then if it absorbs red, cyan, dye color is cyan, it absorbs red, then blue and green is reflected. Means if you are seeing cyan color is nothing but it has absorbed red color, then it has reflected blue and green combination is cyan color, right? If you are seeing on white paper magenta color, on white paper, then definitely it has absorbed green, then it has emitted reflected blue and red color, right? If you are seeing yellow color on any paper, then it has absorbed blue, then it will reflect only red and green. That combination of red and green will yield yellow color. If you are observing black on any of the printing paper, then definitely that has absorbed all colors. There is no light is reflected from that part of the paper. That's why you are observing black color, right? Then the subtractive primaries are the primary colors which the artist working in conventional media must use. The subtractive primaries are the primary colors which with which the artist working in conventional media must use, beside the range of colors that can be produced by mixing the primary colors paint, right? You can use primary colors, any primary subtractive colors, then you can mix any color, then you can find the range of different colors by mixing different quantity of different colors. Definitely some quantity, X quantity cyan, Y quantity magenta, then Y quantity yellow, Z quantity yellow. If you mix with a different quantities, definitely you will get a different shades of those color. This is how the color model in OpenGL will work, right? Then the color model, these RGB colors can be shown in unit cube. Those can be shown in a unit cube. This is RGB color model. This is X. In X direction there is R, then Z direction there is a blue, in Y direction there is a green, right? Then at the origin there is a black. If you don't mix anything, means in your monitor, you see the monitor, if there is no light on your monitor, normally monitor looks black. All the monitors, whatever monitor you take example, all the monitors basically are black, means there is no light, there is no color you are transmitting on those dots. That's why at origin there is a black, right? Then exactly at diagonal you see the white, means you have mixed equally green, you have mixed equally red, you have mixed equally blue, right? If green is 1, red is 1, blue is 1, if you mix 1 1 1 1 equally, then definitely you will get white. That is a diagonal dot, that is a white color. Then on green line, the red is 0, then green is 1, then blue is 0, that is green. Only if you mix among these three colors, only if you mix green, only you will observe green color. Only if you mix red, you will observe only red color. Only if you mix blue, only you will observe blue color. Means only if you transmit blue light, you will see only blue light. Only if you transmit red light, only you will see red light. Then if you mix uh, green and blue, you can see the cyan. This is what with the cube they have shown, unit vector cube they have shown. Shades of a gray are represented along the main diagonal of the cube from the origin black to the white vertex, means shade. And from black to white you can vary the shade of those colors, means how much amount you start mixing those colors, it will give different shades towards white. This is what RGB. Similarly CYM, right? Similarly CYM is x-axis, y is z-axis, then magenta is y-axis, right? Again same. Basically if you don't mix anything, that is white. Normally paper, means this, as I told, CIM we are using it for printing. Normally when you are printing on white paper, normally means you are not printed anything, at that time it is white, means you are not mixed any color, that time it is white, means at origin it is white. If you mix equally all the colors, CYM, if you mix all the colors equally, then you will get a black, that is a diagonal dot, you can see that is a black color if you mix equally, right? Then as similarly, only if you mix yellow you will get yellow, if you mix cyan you will get cyan, if you mix magenta you will get magenta. Again combination, right? Magenta and cyan, if you mix magenta and cyan you will get blue, if you mix yellow and cyan you will get green, if you mix magenta and yellow you will get red. Again same combination. This is COM color model. Positions within the unit cube are described by subtracting the specified amounts of the primary colors from the white light, means from white light you start subtracting the primary colors, automatically you will get other colors, right? This is regarding color model.